Welcome to the podcast. This is Mr. White.
And Mr. Sadler.
And today we're going to talk very specifically about Hooke's Law. So, Mr. Sadler, what do we do in today's investigation?
We use some springs, and we learned that the stretch of the spring has a relationship to the length.
So, we stretched some springs.
With different masses.
And so we used some different masses. And if we hung a really lightweight from our spring, what could you say about the stretching?
Not as much as more mass.
So if we had a huge weight,
much more.
So we have a lot more stretching in our spring. I suppose that makes sense.
And if you have too much weight, too much mass, and you have the spring that's destroyed.
Yeah, then you have a piece of wire.
Right.
Right. So Hooke's Law is named after Robert Hooke, who was actually known more as a biologist than he was a physicist. He did not invent the microscope, but he was the first to see the promise of the microscope, drew a lot of pictures of some invisible things like cells and paramecium and some other biology things that don't really interest me. And Hooke was one of Sir Isaac Newton's major rivals. It's hard to think that scientists have rivals, but him and Newton did not get along, and Hooke kept this law a secret because he didn't want to deal with Newton. And one of the reasons why he kept it a secret was to avoid the conflict with Isaac Newton. The other reason was he wanted to see what kind of applications this had before he just started spouting off about it. So according to the book, what is Hooke's Law, Mr. Sadler?
According to the book, it says the restoring force exerted by a spring, and it says it's directly proportional to the distance of the stretch or the compression of the spring. So directly proportional, that should say something about the shape of the graph, correct?
Yeah. It is directly proportional to the stretch.
Or compression. Because some springs, like at Great America, the springs compress rather than stretch, right?
Right, it's a safety device. So I changed one major thing. Instead of spring, I went ahead and used the word elastic. And so this chapter, we seem to be using the word spring, but this also applies to any elastic object.
Correct.
So an elastic object is something that returns to its original shape, and a spring, of course, would qualify. What other elastic objects might there be?
Oh, rubber bands.
Okay.
Tire inner tubes.
Sure. Yeah.
Many other elastic things.
Bungee cords.
Springs. Shocks on a car.
Yeah.
Even air under pressure would actually return, right? Like a chamber that had an air, like we did
like
in
a piston.
Yeah, like a piston.
Yeah. So all that verbiage says that the elastic force is equal to negative kx. So force we know all about. K we're going to have to revisit.
Spring constant.
Spring constant. This is measured in newtons per meter. So how much force is required to stretch or compress the spring? 1 meter. That's all that is. And x is the distance stretched or compressed.
So this is a force. This is different than the spring potential energy that we've talked about. You can see there's some components of that missing here.
Yeah, but first of all, the x term is not squared.
Correct.
There's no half. And one nice way to do this is to verify units. Newtons per meter times meters. Well, the meters would cancel out, and you're left with newtons, which is exactly what force is measured.
Right on.
This negative sign is kind of obnoxious. And it has to do with the term restoring. So what's happening here? So if we go back to our experiment, we have this nice spring, and from the end of it, we have this weight hanging from it. Okay? If we were to maybe just draw a free body diagram of this situation, is there anything going on horizontally?
No.
No, there's nothing happening there. But vertically, there's two things happening. What is one of those things?
Well, the one thing is gravity is pulling down on the mass and stretching the spring.
So, the weight of the object is pulling straight down. Not the mass, the weight
Correct.
of the object. And the other thing is this elastic force. Because if this elastic force did not exist, then
It would just fall to the earth.
it would just fall to the earth, right?
There has to be an equilibrium here.
So this force is upward in this case. It's trying to pull the object up. Not that it wants to pull the object up, it's trying to resist the shape change. And so this negative force is always resisting the shape change. And so if we do this, is my system, is it accelerating?
No.
No. So we can go way back to when we started talking about Newton's first and second laws. We can talk about equilibrium.
Right.
And so the up force is equal but opposite to the
Right. The forces
down
are
force.
balanced.
Yeah. So the elastic force is minus the weight force is 0. So hey, the elastic force and gravity and the weight of the object have to be the same.
Correct.
And so if we continue that train of thought, we would say, well, negative kx is mg. And we say we can't get away with some things. Like we can't get away with canceling mass because there's no mass term over here. We've gotten somewhat used to that. And the spring constant here, this thing is actually calculated by dividing out x. And actually, I'm going to divide out negative x. We'll talk about why we do that here in a second. So we see this term. This is a nice way to determine the spring constant of any spring. So maybe the springs you use today in class. Of course, this lends itself to a nice graph, which we'll talk about in the plus podcast. Why is this negative sign okay? And that's a good question. Let's talk about the weight. When you hang the weight from the spring, so let's say this is the original shape of the spring.
Right.
The weight is displaced in which direction?
Downward, right?
Down. So
Correct.
from here to here, this is x, but actually it's negative x.
Right.
And we have to account for the negative sign because force is a vector.
Right.
Okay? So the easy thing to do, by the way, is for many of you just to ignore that the negative sign ever existed. And that is not a correct mathematical operation. It's a convenient one, but not a correct one. So let's make sure we keep track of these negative signs, know why it's there, see how it goes away. Now, if it was the compressing kind of spring, okay, then this would be a positive x and things would be different.
Because it restores in the opposite direction.
Right. So this restoring force is trying to restore it up, so we would get a positive value. If this were a compressing spring, it would try and be restoring it down, so it would be a negative value.
Right.
So these negative signs, of course, they make sense. We just don't bring them out when it's convenient. We don't get rid of them when it's convenient. So you guys have created some graphs, and we're going to talk about more of the slope and what that means in the AP Plus podcast. But I believe this covers Hooke's law and spring forces. Pay attention to your units and start thinking about some applications of this as it pertains to roller coasters. So signing off, this is Mr. White.
And Mr. Sadler.